Okay. Hello, everyone. Good afternoon, good evening, and welcome to another set of DIMAP seminars. So the first speaker of this term is Pranabendu Misra from the Chennai Mathematical Institute in India. Pranabendu completed his PhD from the Institute of Mathematical Sciences in Chennai in India, following which he was a postdoc at University of Bergen in Norway and MPI Saarbrücken. Pranabendu is a very versatile researcher with some exciting work spanning parameterized complexity, approximation algorithms, matroid theory, streaming algorithms, and more recently, algorithmic game theory. So we're very happy to have you here, Pranabendu. Also welcome to Warwick. And today, Pranabendu will be talking about an optimal approximation algorithm for feedback vertex set in tournaments. So Pranabendu, whenever you're ready, over to you.
Okay, yeah, so I can just start right now. Thank you for having me, and thank you for the nice introduction. Yeah, so yeah, I'll be talking about an optimal approximation algorithm for feedback vertex set in tournaments. Yeah, so just to remind you what the problem is. So this is the classic feedback vertex set problem. So your input is a directed graph, so maybe something like this. And so this directed graph has many cycles. So I don't know, maybe this is a cycle here. And your objective is to basically get rid of these cycles by removing a few vertices. So in this example, if you remove these two vertices in yellow, then the remaining graph is acyclic. I at least hope so. So this is a very well-known problem, and it's known that it's NP complete. And so I think Paul Seymour gave a log n factor approximation for it roughly 20 years ago, and that is the best thing that we know about it, like the best known approximation algorithm for it. So we are not going to study the problem in general digraphs, but in a specific class of digraphs called tournaments. So in tournaments, so they look like this. They're basically a directed version of a click. So you have an edge between any two vertices, and so actually you have exactly one edge between any two vertices, and then this edge has some direction, like from U to V, or from maybe V to U, whatever. So, and again, your object, so the problem that you want to solve is the same. You want to eliminate all cycles in this tournament by deleting as few vertices as possible, right? So the problem remains NP complete even when the input digraph is a tournament. But at this point, you can actually easily get a 3 approximation algorithm. So this follows from this simple lemma, which says that a tournament contains a cycle if and only if it contains a cycle of length 3, right? And how do you prove it? So, well, like there are many ways of doing it. So a simple way to do it would be take any cycle, and let's say that this is the smallest cycle, right? So then if it is not a cycle of length 3, so which I will call them, I'll call them triangles, by the way, during the talk show, so because they look like a triangle. So if the smallest cycle is not a triangle, then look at these two vertices, right, which are like one step away in this cycle, right? And look at, so since this is a tournament, there should be an edge between them, right? Now, consider the direction of this edge, right? If it is from U to W, then you actually have a triangle, and which also happens to be smaller than the smallest cycle. Or it's from W to U, in which case you have a cycle which is actually smaller than the smallest cycle. So that sort of contradicts your choice of starting with the smallest cycle, right? So this means that this tournament has a cycle if and only if it has a cycle of length 3. So if you take a tournament and eliminate all cycles of length 3, then so you have basically eliminated all cycles in it. And this fact sort of gives you a 3 approximation algorithm. Well, take your tournament, find a cycle of length 3, and remove all 3 vertices of it. And this is a factor 3 approximation because you know that you have to pick at least one vertex of this triangle, and you're picking 3 vertices. So you're not doing worse than factor 3. Right? So this, I hope, is clear to everyone. Right? So now, so the question becomes, what is the best approximation that we can achieve? And there is a more or less an easy reduction from vertex cover to this problem, which preserves, so which basically tells you that you cannot do better than factor 2 in polynomial time, right? So the unique games conjecture implies that the best approximation ratio for feedback vertex set in tournaments is a factor 2. And what we have seen so right now is that there is a factor 3 approximation. So like researchers have been trying to get closer and closer to this 2 approximation. So Kai et al. Gave a 5/2 approximation for this problem using a more complicated algorithm. And then in ASA 2016, so there was a 7/3 approximation. So this was a far more complicated result. It relied on a technique called iterative rounding. Okay, so and other than this problem, so people have also studied some related problems like feedback arc set in tournaments. So where instead of deleting vertices from the tournament, you're deleting arcs. So this problem actually has a p-task. So like you can get a 1 plus epsilon approximation algorithm in polynomial time, roughly like n raised to epsilon time for any epsilon, right? So in some sense, it's a lot easier, like from an approximation factor point of view, it's a lot easier than feedback vertex set in tournaments where we expect a lower bound of 2, right? And the more general feed vertex set problem, so where the input graph is not a tournament, so for that any constant approximation has been ruled out, right? So like this alpha has to be a function of let's say the number of vertices. So the best we know was order log n log log n, and we also know that you cannot have 100 approximation like a factor 100 or a factor 1000 or anything like that. Okay, let's now so like one of the long-standing open problems in this line of research in some sense was that is there actually a 2 approximation algorithm for feedback vertex set in tournaments, or like is there a better lower bound in some sense, right? And we answer this question in our work. So we actually give a 2 approximation algorithm for this problem. So this paper appeared in SODA 2019, and it was a joint work with Daniel Lokstanov, Fahad Panol, and Saket Saurav, Joydev Mukherjee, and G. Philip. Okay, so now I will go ahead and just tell you what the algorithm is. So it's a very simple algorithm, and I'll be able to present the entire algorithm basically in this talk. So this is unlike, I guess, many other papers which are very long and require lots of stuff. So this is something that that can be understood by like an undergraduate student who has just done algorithms. Okay, so let's start with some simple ingredients that are required for our algorithm. So the first is this observation that if you have an acyclic tournament, then so this tournament has a unique topological ordering. So by a topological ordering, what I mean is that you can put down the vertices from left to right, so that every arc of your diagraph is directed from left to right. So you don't have an arc that goes from right to left. And the proof of this is basically like a greedy algorithm, right? So you find, so it's a tournament, so you can prove that there is a vertex which has no incoming arcs. So that becomes the leftmost vertex of your topological ordering. And then you recursively solve the remaining. Okay. So the second ingredient is basically a slightly tweaked version of this lemma we saw before, right? So before we said that a tournament has a cycle if and only if it has a triangle. Now this lemma says that a vertex in a tournament is part of a cycle if and only if it is part of a triangle, right? And the proof is again like the same thing. So this time we're focusing on this vertex U, and let's consider the smallest cycle that contains U. So if that smallest cycle is a triangle, then we are done. Otherwise, just look at this larger cycle and then look at this vertex that is like one step away from you, right? So this vertex W over here, and then look at the edge between these two vertices. So depending on the direction of this edge, either you have a triangle or you have an even smaller cycle. And the second case, I mean, both cases are basically a contradiction to the fact that this was the smallest cycle continuing here. Right. Okay, and the third thing we need is basically, it's a trivial observation that, so consider the instance that is given to you. And let's say SOPT is the optimum solution to this instance. Now, if SOPT already contains at least half the vertices, then you know that the entire vertex set is a 2 approximate solution, right? So therefore, we can assume that the optimum solution has at most n by 2 vertices. So here n is the number of vertices, right? Okay, so we can assume that the instance we're dealing with satisfies this condition. So if it, so okay, so I guess we will see later how to basically get this thing for free. So under this assumption that the optimum solution has at most n by 2 vertices, let's look at the structure of the graph, right? So let's say R is the remaining vertices when you delete this optimum solution, right? So here sits the optimum solution, and here is R. And this set R contains at least n by 2 vertices, right? Now, so since we don't know the optimum solution, we do not know R, but we know that it exists. And we know that it's an acyclic tournament, right, on n by 2 vertices. So given that it's an acyclic tournament, we know that it has a topological ordering. And let's just write down the vertices of R in this topological ordering. Right? After that, what we do is we just partition R into roughly 3 equal pieces, right? And since okay, so since R contains at least n by 2 vertices, and we have partitioned it into 3 parts, so each part contains at least n by 6 vertices, right? Okay, so then let's look at a vertex in this portion R2. Right? So what are the properties of the vertex that we have here? So this vertex, it's not present in this particular optimum solution as well. So there is some optimum solution that excludes this vertex. This vertex also has n by 6 in neighbors, and it has n by 6 out neighbors, right? So all the vertices in R1, they have basically edges going to this vertex, and all the vertices in R2, they have edges going, they have edges coming to them from this vertex. So this particular vertex has at least n by 6 in neighbors and n by 6 out neighbors. And the number of such vertices is basically n by 6, right? So, yeah. So are there any questions about whatever I've said so far? Okay, so then let me just go ahead. So this is what the picture sort of looks like right now. So we have this hypothetical optimum solution SOPT on n by 2 vertices. And then the rest of the graph is a topological ordering using which we partitioned it into 3 parts. And we're looking at vertices in the middle part. There are n by 6 such vertices. They have n by 6 in neighbors and n by 6 out neighbors. Now, if we randomly pick a vertex from the graph, right? Like we sample a vertex uniformly at random, then we know that with probability 1 by 6, we will get a vertex which lies in this set R2. Right? Now, we will call such a vertex a pivot. And the key properties of this pivot are the following, right? So there is an optimum solution that excludes this vertex V. And this vertex has at most 5 by 6 in neighbors and at most 5 by 6 out neighbors. So roughly, if you look at all the vertices in R1, they are all in neighbors to this vertex V, right? So the number of out neighbors of this vertex, so the out neighbors can only lie in SOPT or in R2 itself or in R3, right? And they'll all add up to at most 5n by 6. Similarly, the number of out neighbors would be at most 5n by 6. Yeah. Now, using the first fact that there is an optimum solution that excludes V, So what we are going to do is basically this. So we are going to randomly sample a vertex, and we are going to assume that this sample vertex happens to be in R2. And this assumption is correct with like probability 1/6, right? So we will assume that we have correctly sampled it. And then based on that, we know that so this vertex is not present in some optimum solution, right? So this means that if we look at any triangle that contains this vertex, like so let's say this triangle, right, u v w, so we know that v does not go into the optimum solution. So either u or w, or maybe both of them go into the solution. So what we do is, once we have sampled this vertex v, we just go through all the triangles that contain this vertex v, and we add both these other two vertices of the triangle into our approximate solution. And let's call this set AV. Right. So we keep adding vertices to this set AV until there are no triangles left that contain V. Okay. And at that point, we can conclude that actually there are no cycles in the graph that remains which contain this vertex V. Okay. So at this point, the picture sort of looks like this. You have this vertex V here. On this side, you have the in neighborhood of V. On that side, you have the out neighborhood of V. So let's say that the in neighborhood is, or whatever survives of the in neighborhood is this set V1, and whatever survives of the out neighborhood, that is V2, right? And we just argued that the size of V1 and the size of V2 is at most 5n/6. And whatever, like any cycles that remain in this graph at this point, they're all either contained completely in V1 or they're contained completely in V2. Right? So then what we are going to do is basically recursively solve these two instances, and they will give us two approximation solutions, right? A1 and A2. So my output solution would be simply the union of all these three things: AV, A1, and A2. So let me just go ahead and sort of start to analyze what is happening here. So with probability at least 1/6, the vertex V that we sample happens to be in R2. So the vertex V happens to be a good pivot, right? And let's say we take the optimum solution and we break it into three parts. This part SV are essentially all the vertices that lie on some triangle which contains the vertex V. Now S1 are all the vertices of this optimum solution that lie in the portion V1, and S2 are all the vertices that are from V2. Right? Now, if you look at the the tournament induced by V1, which is GV1, and you look at an optimum solution for it, so you know that S1 would be a solution for G of V1, and let's say S1 star is an optimum solution for G of V1, then you know that the size of S1 is at least as much as S1 star. Right? The size of S2 would be at least as much as S2 star, where this is an optimum solution for G of V2. And of course, when we constructed A of V, we know that we have picked at most twice of S of V many vertices, right? Because from each of those triangles, we picked two vertices. Okay, so now what we did in our algorithm was that we picked V, then we constructed A of V, and then we obtained V1 and V2, and then we recursively solved the problem on G of V1 and G of V2. And these two recursive calls would return two approximation solutions, A1 and A2. Now, if you compare the size of A1 to the size of S1, so what you get is that the size of A1 is, so this is a two approximation. So this is at most twice the size of S1 star, but then that is at most twice the size of S1. Right? And the same holds for A2. So therefore, if you take A of V union A1 union A2, so then the size of that would be at most twice the size of S1. Right? So we have a lot of randomness, like we have a lot of random events going on here, but if all of those things work out correctly, then we do end up with a two approximate solution. So what remains to show is basically what is the probability with which these things happen, and how do we make sure that they are, so the probability of success is constant or something like that. So what we are going to assume in our analysis is that these two recursive calls that we make, right? So these recursive calls are made on two graphs which have at most 5n/6 vertices. And we're going to assume that these recursive calls, they succeed with probability half. So this is something we will essentially prove by induction, right? So the induction hypothesis says that if you're looking at smaller graphs, then on those graphs, our algorithm succeeds with probability half and outputs a two approximate solution. And using this fact, we are going to prove that the algorithm actually finds a two approximate solution for this graph, the current graph, and that happens with probability half. So if we show this, then we are done, right? So are there any questions or comments or something? Okay, so let's now go and basically just analyze the probability of what is happening. So under this assumption that the recursive calls succeed with probability half, with probability like 1/24, this set that we compute, right, A of B union A1 union A2, that is a two approximation solution for the current graph G, right? And this 1/24 is simply that with probability 1/6, you picked the correct pivot, and then with probability half, the first recursive call succeeded, and with probability half, the second recursive call succeeded. So you just multiply them, and with probability 1/24, this process succeeds. Right? So essentially, we have this lemma that if we randomly sample a vertex V as the pivot, then with probability 1/24, at least 1/24, we get a two approximate solution. Now, all we have to do is just boost this probability to half, right? And to boost this probability, all we have to do is just repeat this lemma a certain number of times. So let's just repeat this lemma 20 times, right? So what it means is that we sample 20 random pivot vertices, and for each of them, we compute this A of Vi, and then we make two recursive calls, and then like combine the solutions that we obtain. So for each pivot Vi, we obtain a solution Ai. Okay? And then what we do is we just output the minimum solution as our approximation solution for G. Okay. Now, the probability that we fail to find a factor 2 approximation in all these 20 attempts, that is at most 1 minus 1/24 raised to 20, which is at most half. Right? Actually, it's strictly less than half. So we have shown that with probability at least half, we are able to obtain a two approximation solution to the input graph. Right? Now, yeah, so this is the lemma that we have shown. Now, the next question would be, what is the running time of this algorithm? Right? So, like if you look at one step of the algorithms, and what we have done is we have taken a graph on n vertices, and then we sample some 20 pivot vertices, and using those 20 pivot vertices, I make some 40 recursive calls, like 2 for each pivot vertex. And then we combine the solutions received from this recursive call, which takes me some time, maybe order in quick time or something. And so you can write down this recurrence, and then the master theorem tells you that the running time of this recurrence is n raised to 21, which is a polynomial in it, right? And this is our result, essentially, that there is a randomized polynomial time algorithm for feedback vertex set in two numbers that outputs a two approximation solution with probability at least half. So in our paper, we actually also show this for the weighted version of the problem. So that requires some more work and some more tricks. Also, the running time sort of goes up a little bit. And then after the conference version was out, we submitted it to a journal, and then in the journal version, we did some more work, and we were actually able to improve this. So for example, for the unweighted case, the running time came down to n/10. So we had to basically optimize a whole bunch of parameters. Like instead of saying that the recursive calls or this probability is half, we say it's 3/4 or something like that. And then we have to also optimize on the number of pivot vertices picked and so on and so forth. So if you do all those things, then you can actually improve the running time to something like n/10. Okay, so this is basically the algorithm. This is basically the technical content of the talk. Yeah, so at this point, yeah, I'm happy to answer any questions here.
Pranabendu, could you comment on what techniques you use for the weighted version?
I'm sorry, can you repeat the question?
So what is different in your algorithm for the weighted version? What more do you need to do?
So for example, let's go back here. So like we have this lemma, right, that says that if the optimum has at most n/2 vertices, then yeah, we already have a 2 approximate solution. Otherwise, we can use this assumption to say something about the size of R here, right? That R contains at least n/2 vertices. So all of these things do not work in the weighted version because you're not counting the number of vertices, but rather the weights of the vertices. So to handle that, you basically need a different kind of lemma here, which says something about the weight of the vertices, or something about how the heaviest and the lightest, let's say n/6 or n/3 vertices, how do they behave with respect to the optimum? And based on that, you basically get a different size of S and different size of R, and then that affects a bunch of calculations and stuff like that.
Okay, thanks.
Like I don't have the calculations with me on the slides, so but yeah, you can just look at the paper and it has all the details, and it's also very
Okay.
easy to read.
Okay.
Okay, so after our work was published, so basically, so you can think of this problem as some special cases of hitting set. So essentially, you have a universe and you have a set of, let's say, D size tuples of this universe, and your objective is to find a subset of elements which occur in every one of these tuples, right? So it's specifically feedback vertex set in tournaments is a special case of this 3 hitting set problem. So each triangle is a tuple of size 3, and you're trying to hit all these tuples. So what we know is that for general 3 hitting set, you cannot actually get a better than factor 3 approximation algorithm. However, for special cases like feedback vertex set in tournaments, we indeed have 2 approximation algorithms. So we also looked into, what other special cases of 3 hitting set have like 2 approximation or something close to 2 approximation algorithm. So we considered split vertex deletion, and we showed that it actually has a 2 plus epsilon approximation algorithm, which was improving upon a 2.5 approximation before or something. And then so this was also very similar to the algorithm I showed you, but it was like much more involved. So we had many more cases to sort of work through. But then some other authors basically published a much simpler version, which is also deterministic. So using some structural properties of split graphs, you sort of easily get a 2 approximation for this, well, 2 plus epsilon approximation for this problem. So okay, and then another special case was cluster vertex deletion, which was also recently solved. So what is open essentially is getting a deterministic 2 approximation algorithm for this problem. So our result is basically randomized, and since we pick a random pivot and then do some stuff with it, so it's sort of hard to get rid of this randomization. So the best we know is some sort of a quasi-polynomial time deterministic algorithm which gets the same to approximation. So it seems that it should be feasible to get a deterministic polynomial time to approximation, but we just don't know how to do it. Another open problem would be essentially to consider more special cases of through approximation. So this property that there is a cycle if and only if there is a triangle, it holds for tournaments, but it also actually holds for more general classes. Like if you think of something like a directed chordal graph, so the underlying undirected graph is a chordal graph on which you put some direction. So this property that cycle implies triangle is also true there, but we don't know of a better than two approximation algorithm for this problem. So this is also something that you can look into. Thank you.
Yeah. Thanks a lot, Pranabendu, for the nice talk. It's a very elegant algorithm. Do we have any questions for Pranabendu? Feel free to unmute yourself or just type the question in the chat.
Thank you for the talk. Can you say something about this, the randomized algorithm, and how do you achieve quasi-polynomial time?
Okay, so I've forgotten the answer to this. So essentially, we have to pick a vertex V. So what we do is we use what are these things called? Some sort of hash function families, basically. And we show that there is a family of quasi-polynomial size which contains a function which will map, like, so any hash function maps vertices to some 3 classes, right? Or something like that. So one of these functions will actually pick out a vertex from R2 as a specific thing.
I see. And do you know if this approach has some barrier, or can you make it polynomial?
I mean, so the family of hash functions that we use is basically something that's very well known. I mean, with some tweaks, basically, you select some primes or something. So we don't expect that approach will directly give you a smaller family of hash functions or something like that. Or maybe it will, but I mean, we don't know how to do that.
I see. Okay, thank you.
Thanks, Igor. Are there any other questions? So I have a quick one. So yes, okay that we cannot do better than 2 approximation in polynomial time, but if I wanted to understand the trade-off between the running time and this approximation ratio, on let's say on one end you have this 2 approximation in polynomial time of yours, and at the other end, an exact algorithm in, I guess, 2 to the n time or some c to the n time.
Yeah.
So what would be the right question to ask if you wanted to understand the trade-off? Do you think there could be a nice gradient that tells us that, here's the trade-off between the running time and approximation ratio?
I mean, so yeah, so you can try to do some sort of parameterized approximation. So I mean, so this work actually came about because we're trying to solve the parameterized problem, but we just happen to observe that this actually gives us a very nice approximation algorithm for this problem. So you can try to do some sort of a parameterized approximation for this problem, and then I guess you interpolate between the approximation factor. You'll have a trade-off between the approximation factor and the running time that you get. I don't know of exactly anything in this direction, but
so what exactly was the question you were trying to answer? Sorry, Pranabendu, go on. I'll let you finish.
No, I thought your question was there. What do you expect to get if you allow some sort of exponential time in there?
Yeah.
So,
I mean,
so I think so some sort of parameterized approximation algorithm would work here, like so something maybe inspired by vertex cover or something, right? So maybe you can adapt some of those methods to this problem.
Okay.
Like this problem is roughly can be considered as equivalent to vertex difficulty. Like the approximation hardness or many other things just come from vertex in some sense. So I would expect that it behaves in the same manner even when you have FPT approximation.
I see. Okay, thanks. That helped. Are there any other questions? If not, let's start Pranabendu again. Pranabendu, thank you for joining us. Well, thank you all for joining, and I look forward to seeing you all at the next DevMath seminar. Thank you.